climb speed, you're going up the fastest, but the distance is getting from the start is getting longer and longer. So what you want is best angle speed, and that's why you end up getting that. But notice these two, you know, are pretty straight line, but these two aren't. Where they come to a point, I think that's in here someplace. Yeah. Where they come to a point, the altitude where they both come together is the ceiling of the airplane. That's as high as it's going to go. Okay? Generally, most propeller-driven airplanes, this is pretty straight up and down, okay? It may have a little slope to the left. It may drop a knot or so with 2,000 or 3,000 feet. Jet airplanes, on the other hand, it's more like this. I mean, for instance, I first started flying, my first solo airplane was a T-37 jet trainer. And on the T-37, to get best rate climb speed, every 1,000 feet, you reduced your climb speed by 2 knots. So every 1,000-foot altitude, you slowed the airplane down 2 knots to get best rate climb. On this Saratoga, you know, this curve is practically vertical. This one is not. I say it changes. Notice that it's pretty slow at sea level, but as you go up in altitude, it gets faster. Now we have defined another term for single engine airplanes and for all airplanes. We call it the service ceiling. The service ceiling for a single engine airplane is the point at which you only have 50 feet per minute rate of climb. I'm sorry, take that back. It's 100 feet a minute for a single engine airplane. It's 50 feet a minute for a twin or a multi-engine airplane. That's called the service ceiling. Where those two come to a point, that's the absolute ceiling. Well, generally in climb testing, the plots that we looked at, these plots that I showed you, are primarily to determine the best rate of climb and best angle of climb speed. That's what we use them for. We don't try to determine the rate of climb for certification purposes using those. We will take this curve and we will use that to do, you know, those speeds to do an actual set of opposite heading climbs to do that. And then at the maximum rate of climb, we will determine a rate of climb and maximum rate of climb versus altitude. And that will be used to show generally the sea level value. Remember I said that it should be at least 10 times the stalling speed in miles per hour to pass the FAA rules for this kind of airplane. Today, they've changed that. If you read today's regs, it's 11.5 times. Why do you think they made that change? Some years ago, they changed miles per hour. A hint. They changed miles per hour to knots. Okay, 1 mile per hour or 1 knot equals 1.15 miles per hour. So instead of 10 times the stall speed miles per hour, to 11.5 times the stall speed miles per hour. It's actually the same requirement. They just changed the numbers a bit. Okay, now let's look at this from the standpoint of just energy. We'll determine what we call the excess specific energy, or P sub S. You may have heard that term. It's come into use, probably in the past 30, maybe 40 years, PCBS has. And if we say that the total energy possessed by an object is the sum of its potential and its kinetic energy, then we can write that equation like this. So the total energy is equal to the mass times the gravity times the height. Okay, that's the potential energy, plus 1/2 mv squared for the kinetic energy. Then the specific energy in feet, and specific energy, h sub e as it's called, in feet, and that's the units are in feet, can be obtained by dividing that previous equation through by the weight of the vehicle. So we have this one, if we divide through by the weight, we get this. So the specific energy is equal to the height plus v squared over 2g. And then if we differentiate that with respect to time, dhe dt, we end up with this term we call excess specific energy, P sub s. And notice that P sub s is just equal to dh dt, we know that's rate of climb, plus v over g times dv dt, which is the acceleration term. Right, so we've approached this rate of climb problem from two different angles and ended up with the same result, essentially, okay? That equation only differs from the equation 6 by the weight term. If we divide equation 6 by the weight, we have thrust horsepower in excess over weight is equal to P sub s. So P sub s, the only difference between it and thrust horsepower in excess is just the weight. Questions?